Let's go ahead and go on to collections. We talked about arrays, which is a type of container, but there are many different types of collections. Now, remember, with an array, the nice thing about arrays is you can hold primitives like integers, but with everything else, you must have an object. So the idea of a collection is going to hold one item at some location. A list keeps them in order. A set basically says there's no duplicates and no ordering. And here's how it's really laid out. A collection is either a list or a set. If it's a list, it's basically either an array list or a linked list. We don't use vector anymore, so ignore that. And then if it's a set, it's either a hash set or a tree set in general. And we'll talk about a linked hash set a little later. So again, the container cannot hold primitives. You have to be wrapped. You have to do some casting if you don't use generics. But Java does do runtime checks, and you can have a class cast exception. Let's see. Do you understand what I don't think we've talked about generics that much. We should have. Do I have a list fun in here? I don't. All right. We're going to call it list examples with only one T. Okay. Public static void main string args. All right. So we can create a list. I'll just call it list for lack of a better term. And new, we'll go ahead and create an array list. All right. Yes, java.u. Oh, I clicked the wrong button. One moment. Let's do that again. Import the class. Import that guy. Good. Get the array list. Good. All right. So a regular list, we just say it's an array list. And what is an array list actually using behind the scenes? An array. Okay, good. Everyone's on track. All right, good. Now notice that we can do a list.add of an object. If we can add an object, what does that mean we can add?
So if you can add an object, you said?
Yeah, isn't that what I just said?
Yeah.
Add object.
Yeah.
So what does that mean we can add? Anything that is an object. So we can add student. And we can even add hey, let's go. Can we add a moat? Let's see if it takes that. Hey, we can add student and moat. Can we do that with an array? No. Not really. Well, there are ways to do it, but if you have an array of objects, it works. But that's not how you like use arrays. So in a generic list, where you have something of this nature, you can add whatever you want to it. And then if you do list.get of 0, what is that? Is that the student or the moat? Let's find out. It is the student. It is, isn't it? What does that mean, Tyler? What are those numbers?
Their place in the list.
Memory location.
Right, so this is what the full class name is at this memory location.
Oh, I wasn't seeing those numbers.
It's okay. Yeah, you were thinking these numbers.
Yeah.
It's okay.
It's behind a computer screen down there. I never see the print.
So if I do list.get of 0, and then what function should I be able to call on that? This is it.
Wait, you should be able to call any function that's student head, right?
You would think that, but I can only call functions that are on an object. Why is that?
Wait, what do you mean?
Well, because when they're in a list, they're all just objects.
Right. So in order for us to deal with it, we would have to cast it first to a student by using this syntax. Then you do dot, and now you can do get ID. All right. Gonna go print that out so the ID will come out. All right. But is that annoying?
Yeah,
Super annoying.
very.
Very annoying. So what you can do instead is you use generics, the list of, we'll call it student, call it the SL list equals new array list of student. And now you can do sl.add new student, and I'll go ahead and again add John, and 1, 2, 3, 4. And now if I'm down here and I want to just print that out, I can do system.out.println list.get of 0.get ID. Why did I? Well, that was interesting. Oh, I did the type the wrong one. Let's try that again. sl.get ID. There we go. And if I were to run this, still prints out the ID. Why is it in the second list I don't have to cast it from an object to a student?
It's already a student list.
Right, because you said that this list is explicitly of students. Could I add a note?
No.
No. So there's your trade-off. Let me go ahead and wrap this around with some nice comments so this makes a little more sense. Oop. Public, I'm going to call it generic list. Let me go ahead and static void. So the point here is this is a list of anything. This is a list of only students. I can add anything to list. I can only add students to SL. Now we will print to display the differences. All right, great. Now go ahead and call generic list just to make sure it still does what we just did. Perfect. All right. Any questions on the two right there? That's how you use generics inside of Java. Good?
Yes.
All right.
Oh, by the way, it's National Puppy Day.
Puppy Day? Did you bring any puppies for us?
I wish. That would make my day a lot better. Oh, yeah. I can make a few phone calls and get some puppies up here. Should I do that?
I could go get my puppy.
I wasn't. Yeah.
It'd take about 20 minutes.
All right, so let's think about a list of puppies.
Yes.
Oh, you see what I did there?
Yes.
Good. So we have a list of puppies. A list is basically an ordered sequence accessed by zero-based index. So it's something along the lines, you can add an element to the front, you can put an element in the beginning, you can add elements to the end, you could you can definitely remove elements in the middle if you want to. And this is what we think about when we use a list. So a list is going to manage its own size, so you don't have to do anything. So you can add something at a specific index with some object. Maybe you can get it at index, and then you can print the index of something else as well. So let me go ahead and showcase that a little. I'll go ahead and create another function. Let's see, void, let's see, list basics. Go ahead and create a list, this time of just integers, just to make our life easy. Call it the integer list equals, we'll call it an array list this time. Ooh, that was bad. That's what I meant to do. All right, so for int I equals 0, I is less than 1000, I plus plus, il dot we can add new. I'll just do math dot.
Why don't you do a fill for that one?
Ooh, can I do a fill? Let's find out if I can. il dot fill. Oh, there is no fill.
Oh,
Phil is not with you on this one.
dang it, Phil.
I never liked that guy anyways. Let's go ahead and create a random object.
Oh, we can do it there.
Yeah, because it's a standard array. These are not arrays, they are
Array list.
they're a list.
List.
Yeah.
Which are arrays, right? They use arrays.
Does it have to?
That says array list. So
Yeah, so this list is using an array list. So that's true,
they don't know.
but they may not all. Ran dot next int. All right, so I can add 1,000 random integers to our list. Okay. We'll go ahead and print them out.
Oh, we're gonna print all 1,000 there.
We'll print the first 10. How about that? Does that make you feel better? So that'd be il.get at I. So it's kind of behaving similarly to an array, which is fine. Let's see, list basics. Let's go ahead and call it in main. That way we can mess around with it. All right, so there's some random numbers. Not sorted, but that's okay. All right. Index of. What's index of like? Let's see, let's get this number. Oops, that's not what I wanted. System.out.println. Let's see, il.index of this guy. And I'll go ahead and type the syntax out fully correctly so you know what's going on.
Why are you doing new integer?
Because the list has to contain objects, right? So you need to actually have an integer object. And the integer object just wraps around a regular integer and keeps it as an object. Right?
One more time.
Anyone else want to say that? What's the big I integer object do?
Takes an int and turns it into an integer. Is that what you said?
It takes an integer and turns it into an object.
Okay.
So instead of being a primitive, it's now an object.
Alright.
And a list has to hold objects. Arrays can hold primitives, but a list has to hold objects.
So why wouldn't it wouldn't be an object when you do add new integer?
It is a new object because I'm creating a new integer, right? I create an integer object with some random integer and then pass it to the list.
Okay, then
And then I need to know what's the index of this integer. Where is it in this list?
That's a different new integer.
It's a different integer, but does it contain the same value?
No. Yeah. No.
Well, it contains this value. So I was going to run it and see if it goes ahead and prints it out, and it should. Prints it at value 7, index 7. So find the index of in the list. All right, so we'll just let me comment this. We'll fill out the list with some random numbers. Let's print the first 10 numbers. All right. So what's index of like? What's that on the array side? What is that doing?
Index of?
Mm-hmm. Haven't we seen that?
Finding the index.
Which was like, which one? This guy, wasn't it? Array binary search. So it's like binary search. It does the same functionality, just not as fast. Do you think it implemented with a binary search or a linear search is actually the question I meant to ask. But it's done with a linear search because you don't know if your list is sorted. So this is a slow linear search. Okay. What else do we have? Last index, we can remove. Removes an object at a specific location. Ooh. All right. So let's remove this guy. All right.
So you're pretty much teaching us all the shortcuts of the C++ stuff we learned, right? Like everything we had to do in like this long drawn out process, we just like put dot, remove, done.
That's what Java is all about. Taking all those things you had to do beforehand and just making it a simple function call. And that's what OOP is also about. Taking everything you had to do, put it into a library so you can easily use it. Because now we're using objects so we can easily call the code that does what we want. But we need to discuss how it's organized so it makes sense and everyone's doing, building their libraries the same. Because someone built the library at index of, someone, they did this. We just want to make sure there's commonality so when you go and build your own library, people understand what you did a lot better. But first, we need to keep studying how Java is doing it. And we've gone through some solid principles, and we're about ready to start. I'm going to start talking about them soon, how they apply here. But let's go ahead and remove this. So yeah, it would be, il.remove new integer of that number. Okay. So if I were to print off the first 10 numbers, what should I get? Beforehand it was in index 7. Then what would happen? I'm going to go ahead and make a little difference line here so we can see the difference. Should that number be in the list at that point? No, so it's going to be removed. So is at index 7 where we're removing 130, and 130 is now gone. Notice that everything else has been shifted down, because that negative 127.9 used to be the last one. This guy used to be last on the list. Now he's down up here. And so we just have a function that does that. Why did you do remove inside of arrays in C++? Oh, what did you have to do?
I don't know.
You don't know? What do
I
you
just
have
remember doing that.
Oh. So when you removed an array, what would you have to do?
Like an item in the array?
Yeah, remove it.
You'd have to like move through it and
Shift everything down, right? So this does that for you. Isn't that nice?
They add one into with this one.
Oh, actually, no, that's a good question. Let's do this. System.out.println my size before removal. List.size. Whoops. What do I call it? The il.size. I'll copy this right after the removal. My size after removal. Let's go ahead and run that. That was a great question. Bless you again. My size before removal 1,000. My size after 999. So it actually shrunk it for you.
Well, that's because it's the first 10 of the 1,000.
Yeah. So it actually shrunk the list for you as well. Wasn't that nice? Hunk. All right. So everything previously could be done on a regular array instead, right? I don't know if there's anything I've added besides convenience right now, correct? I mean, the convenience is nice. You hopefully all agree with that. But I haven't added anything else yet. So why would we want to have a list class rather than an array to store our data?
Because you want to store more than, you want to store objects in the list of all different kinds.
But you could create an array of objects.
Different kinds of objects.
Right. I mean, we could just have an array of whatever our different kinds of objects are. But why do we have a list interface? The real question here is, why did I do this? I've been doing this the whole time.
More functions.
Why do I have list il equals array list as opposed to just array list? Why am I using list by itself? I mean, specifically, you go back here and you have list right here. Why am I using this interface instead of array list?
So that you can use array list, linked list, and vectors.
In vector, why would I want to change that?
Change
You
what?
want to have like what, a list of students and things or something?
Okay.
Because
Like,
all
so
of
if you
those
wanted
can
an
be
array list in a
objects?
list,
Hmm?
could you have like the array list in a list? Is that what?
Well, if I have the code written this way, and all of a sudden I decide I want to use a linked list instead, what do I have to change?
Just type out.
New link list. Done.
Does everything else work the same? Right, because linked list is a list, right? So I could use a linked list or array list, whatever I want, just by changing this one line of code. Why would that be handy? And which principle of solid does this adhere to? You will be. I was in an interview and I was just asked this question. No joke.
Hold on. The one about adding stuff. Open close principle.
Okay, it is similar to open close, but that's not exactly it. You're good. What is this like? Remember my analogies. I tried to give you good analogies.
A duck.
For some reason, the duck kept popping in.
The
my head,
duck.
too.
I don't know why.
Now the duck would be saying that the list interface is not correct for the array list, and you need to clean it up. But an array list is a list, so this does adhere to the duck principle. You are correct. I mean, in reality, it's adhering to all 5 of them, but what's the big one that it's adhering to more than anything else? How's this? Remember the dependency inversion principle with the wall socket?
Oh,
What's
And the toaster.
That's the integration,
Oh,
interface segregation principle. That's a good one too. But this one, how is this like the wall socket? Who is the wall socket here?
the list.
The list. And then who's the lamp? The array
Array
list.
list.
Or you could plug in a computer, that would be a linked list. Or you could plug in projector, maybe that's the vector. So this is adhering to the dependency inversion principle. They will sometimes call this dependency injection instead of dependency inversion. But if they ever say dependency inversion, dependency injection, this is what they're talking about. It's the fact that you have an interface and you can just plug in whatever you want depending on what suits the best.
Did you give that example in your interview?
Yeah. Yeah. I said I call it the wall plug principle.
He's probably like, we
What?
know way too much about this.
Yeah. It's like, okay, you got it. Yeah, it's like, all right, you got it. Okay, you can stop talking now. Okay. Okay, so we might implement a list differently under the hood. So let's talk a little bit about the array list. So it automatically expands itself, puts objects with add, can use get, and has a method size, similar to link. So let's talk about the speed of different operations. If you wanted to add something to the list, is that fast or slow? Hey, look, I'm giving you the answer, but
Depends. It depends on where you're putting it.
if you're putting it at the start of a list, is it fast or slow? Why is it slow?
Because it's got
You
to
gotta
move
move
everything
everything
down.
over.
You gotta move everything down. How many iterations are you doing?
It's been easier.
I call it O of n because if the n is the size of the array, you're doing about n iterations. Okay? You'll get used to big O more in data structures. I just want to expose it to you now.
Oh, that was a good show.
Big O? That was a show?
Oh, yeah. Oh, fighting robots, man. Like gun.
Oh, I understand.
Man, we need to make one of those gifs where you have, O of log of n fighting O of n squared or something.
Yes.
And then log of n just destroys n squared.
Yeah.
That would be awesome. All right,
I'll make that happen.
You need to make that happen. All right, how about adding to the end of a list?
It's faster.
It's fast. Why is it fast?
Because you're just
Right
throwing
there,
it in
just
there.
adding a new one.
Right. So how many iterations do you really have?
One.
Right. So we say O of 1. How about adding at some random index?
It depends on what the
Iterate
index
right
is.
through and-
So if it's in the middle of the array, on average you would be in the middle of the array, right? Right. So how many iterations would half iterations n divided by 2? If it's n divided by 2, we just call it O of n. Because it's really 0.5 n. Again, it's just n.
So would it find it and then keep looking in case there's another one
Which one are you talking about?
at given index? Or does
So-
it just find the first one and then it's half?
So that's when you want to add at a given index. Let's say.
Oh, add, sorry. I thought you were
Oh, okay,
just
good.
looking.
You,
Never mind.
you understand add at a
Yes.
given index?
I
So
was
if you had 10
thinking
elements,
five.
you want to add in 5, you'd keep the first 4 and then shift the other 6 down or something like that. Okay, clear is O of 1. Why would that be O of 1?
So we could just get rid of everything.
Well, yeah, you just set the size to 0, right? And then you're done. Get. Why is get what?
Saying get this.
Get at this index, right? So it just jumps to it and then returns it. Again, O1. Find index of an object.
It has to run through the whole list.
That's what I was thinking.
That's what you're
in my
thinking. So
head.
that's O of it. Slow. Removing the first element.
That's terrible.
Terrible. Again, and yeah. And removing last element though?
Not easy. Huh?
Easy. You just decrement the size. We're done. Remove at a given index. Well, that's similar to adding at a given index because you have to do similar operation. So again, slow. You want to set something at index 1 or 0 or wherever? Fast because you just jump to it and set. Okay. Size. Well, you can keep track of the size. Two-string is still slow because you have to go through the whole list. All right.
Why?
That's my least.
The
No, it says
two-string.
why at the end, so.
Why? I was in case we forgot to discuss why all these things are going on. Okay, great. Okay. So an insertion into a full list causes a large reallocation. An insertion into the front slides down everything, so that's slow. Removal also slides subsequent items. So you still need index and subscripts a lot. All right, we're not going to go into the nitty-gritty details of this too much, but it's important you understand conceptually what's going on. The elements of array lists are too tightly attached. We can't easily rearrange them. That's the problem. If we remove something, we got to remove everything else. So we want to detach them, from the first picture to the second picture somehow. So can we break the storage apart into a more dynamic and flexible structure? What's the answer to that?
Yes.
Yes. Why is that always yes?
Because anytime you ask us this reason, you're asking us.
What's the first word?
Can.
And what's the answer?
Yes.
You're an engineer. Yes, you can do anything.
You can do anything you want, but you have the money and the time.
Right, there you go. Right. So the answer has to be yes.
I can build a supercomputer given, a few $1 million in a year or two.
Yep. The reason I say that is because there are very, very, very few problems where the answer to can we is no.
Like that one with the printer example.
No,
No, the
halting
key
problem?
is we. That's the key.
Yeah. It's true. Can you? Oh, definitely. Can we? Absolutely.
Well, no, I
The opposite.
I think she was saying the other thing, but that's okay. We'll keep going. All right. So what we can do is make a node so where each item points to the next one. Why would that break it apart? Ooh. And then we have a slash saying when we've ended it.
Because we just need to find a certain node.
So pictorially, hopefully pictorially this makes a lot of sense. Is that my eraser on the floor? It is.
No, yours is up there.
Oh, I have two erasers. Oh, man. All right.
Success is a teacher.
I'll use this one. So if we were breaking apart in this structure, and let's just say we had 0 pointing to, 20, pointing to a lot of different items, then pointing to 1, 2, 3, 4, which points to, 2, 3, 4, 5. And then that would point to a lot of other items, and then maybe we're ending with, over 9,000.
Yes.
Which is no. If we want to insert 1, 2, 3, 5, pictorially, what would we have to do?
Just put it in there. Just
Double
Insert.
arrow up
So we draw an arrow from here up to,
between 1234 and
so we draw the arrow up to this. All right, then what do we do? You gotta do one other thing.
move everything.
What's that?
I said draw another arrow.
From,
Well, to like from 2345 to in between.
Oh no, it's from 1, 2,
that what you
3,
mean?
4 to.
all we have to do now is
down.
update this to
Oh.
point here. And these two things are pointers. So you just need to change the value stored there. Do we have to change the rest of the list?
No.
No. So we only have to do two things. So instead of having to change everything else, we only have to update 2 memory locations. Is that faster?
Yes.
Isn't that pretty same as just adding it to index?
Well, if you had this as an index,
So is there no index at the
0, well, hold on. 20, I'll just put my ... Then you have 1, 2, 3, 4. And then you have 2, 3, 4, 5. ... And then, oh, 9,000. Okay. Ooh, that's a weird number. That's 9,000. And you want to put in 1, 2, 3, 5. It would need to go right here, right? But before you can put it here, what do you need to do? You got to move all these guys over, right? So that could be a lot. Well, this is just 2 things.
So
right?
how would you identify that now? Like, if none of those have indexes?
Correct. There are no indexes now.
So, okay, pretend those, well,
So
You-
how would you find index of?
yeah, like,
Well, so you can, because wouldn't this be index 0?
so you're going by name.
This is index 0, then this is index 1, then 2, then 3, then 4. It's just how many jumps are you doing, right? That's your index.
So pretty much what we're doing is changing the index. Instead of
Well,
Not changing
moving
the index.
instead
I'm
of
not-
moving all the numbers. you're
there's
changing
no
theirs.
index stored in this list. Index is not stored anywhere. If you want to find the index of something, what would you have to do?
You have to give it an index.
You would start here. This would be index 0. Am I that value? No. Let's go to the next one. That's index 1. Am I that value? No. Go to the next one. Index 2, index 3, so forth and so on, right? Because your index is just how many jumps you've done inside of this list.
Create an index whenever you need it.
Yes. You would have to create the index. They're not actually stored anyway.
Which is why it's easier to change everything.
Yeah,
If you
'cause
have an
there's-
index.
Yeah, there's no index. We took that apart.
And what is that called?
A linked list. This is specifically a singly linked list. Why do you think it's called singly linked list?
There's
You
one
have a
row.
doubly linked list.
Good foresight. How many links does each node have?
Well, I
Oh,
don't know. Oh, no, that's
Yeah.
fine.
It's
No.
linked to 2 numbers.
no.
The one behind it.
This guy only has 1 link. This guy has only 1 link. Yes, he has a link pointing to him, but he only contains 1 link.
So would a double link have arrows both directions?
You got it. So a doubly linked, you would have another one right here going back. And that would be doubly linked.
And what would the point of that be?
So you can go both forwards and backwards.
Oh,
So why wouldn't you always use the doubly linked list?
yeah.
You would always use a doubly linked list. Which would y'all prefer to implement?
Singly.
Right. So we're going to stick with singly because I'm trying to make sure this is clear, because otherwise we're going to be drawing way too many arrows. But yeah, in reality, you use doubly linked list. And that's what a linked list is inside of Java. It's actually a doubly linked list.
And it's faster because it doesn't have index numbers.
Whoa.
Right? It's
Ah.
not faster?
Is it faster?
Yes.
You already told us that answer, I thought.
Well, it's
Is it-
faster for...
Is it better?
Hold on.
To insert that. It's
Yeah,
faster.
it's faster to
That's what I'm
insert.
talking
That's
about.
correct. But is it faster in general?
I don't know.
Don't know yet. That's right. The right answer is
Yes?
it depends.
No.
Well, is it because it's pointing to another number, so then you're gonna have to go find out what that is?
Yeah.
Instead of just like going straight through.
Can you do a binary search on this?
Sure.
Yeah.
Wait, only if it's a.
Can you jump? Well, what's the index? Am I storing the index? Does it make any sense to do a binary search? No, you can't jump to the middle. So you can't really do a binary search on this. But if you're not keeping a sorted list, maybe there's something else that's useful. Okay. Add operation, remove, get, set, index of. Okay. So, if I'm on this guy and I want to add -1, what do I need to do?
Put it in there.
All right, what do I have to do?
Draw an arrow.
From here to,
0.
am I done? Okay.
No,
Right. So adding to the front of a linked list is what?
easy.
Easy. In other words,
Faster than- yeah, it's faster.
it's
than-
fast.
It's fast.
How about adding to the end of a list?
Yeah.
Yeah.
Yeah, I mean, you might have 10,000. Sorry, people watching at home. You might have 10,000. Set that to null. What do you need to update?
Front arrow.
9001 can't have a null.
Yeah, right here. So that's fast. Everyone following me?
Yes.
All right.
So it's fast every way.
Hold on.
Insert.
Add at a given index. Why is that considered slow?
Because it has to be 2 arrows, right?
Iterate for you to get that.
You have to iterate first. That's the problem. If I wanted to add right here, I would need to start from this guy, go, nope, not there yet, not there yet, not there yet, not. Yeah, I found it. Boom, boom, boom. So you still have to iterate n times before you can just insert it. If you knew exactly where you want to insert, then it's just O of 1. But the problem is inserting at a given index, you have to go through the list first. So inserting at a random location is still O of n. Everyone got that? Yeah. Declare it. It's fast. You just, I don't have anything now. You just say, I have no more nodes, and we're done. Get is O of n. Why is get O of n? If I want to get something at an index, what do I have to do? You have to go through it. Hold on a second. So this is slow. What was in an array? Fast, because you just jump straight to it. So now we have two things that are different. Adding to the beginning of the linked list, fast. But it's slow on get. Array, slow on adding in the front, but fast on get. Find index of an object, O of n. Is that the same as an array?
Wait,
Yes.
Yes. Yeah, linear search. Removing the first element, why is that fast?
You just take it away.
You just take it away. Yeah. So that's a significant boost over an array right there.
So
that used
now
to be,
the index, if you just take away the first one, the first index is just null. It's not replaced.
no, it's now 0.
Oh, yeah. Because there's nothing there.
Because in reality, when you have your my list linked list class, it has something called head, and that points to the first guy. So if you want to remove the first guy, you just change this pointer so it points to the second guy. You're done. That was easy. Removing the last is still just as easy because you, in general, keep a pointer to the last element for this purpose, so it's still O of 1. Removing an index O of n, why is that?
you did it right there.
Yeah, you did right through it. Set is now O of n. Why is that? Setting a value at a given index.
Because you have to iterate through it.
You have to iterate through it.
Index.
Size is O of 1 because we just maintain the size as part of our linked list object. To string is still O of n. That's really not going to change. So what has happened here? When would we want to use a linked list over an array?
You want to add things
yeah.
to the beginning and the end.
Right.
We know later we're gonna pass.
And you don't want to do random access. But another thing, if you need to iterate through the entire list, changing different elements, either is sufficient because you're going to just be going through it. All right. How are we doing on time? What time is this class end? 10:50?
I really don't know, honestly.
About 4 minutes.
4 minutes.
I just know I leave.
I don't think we have time for the rest of this. We do not have time for the rest of this. All right, so next time we're going to go into iterators. Make sure you start reading chapter 7 if you haven't already. It's going to really delve into this. We talked about, oh yeah, again. Which big principle is being showcased right here?
Inversion.
Dependency inversion. You got to get the word dependency because it's breaking away the dependency.
Because it,
This depends specifically on an array list. By taking it to a regular list, you are decoupling it, or you're inverting the dependency, or you're injecting the dependency, such that you only have to adhere to a list interface.
Now it's an adult.
Now it's
just
an
a
adult.
child.
Now it's a tiny child. Yeah, there you go. Make sure you learn that. More than one interviewer has asked me this question. They'll usually say, what is dependency injection or what is dependency inversion? It's this. That's what it is.
That's how we're gonna answer that question. It's this.
It's the array socket. It's the wall socket principle.
Yeah.
You don't solder a lamp straight to your power. You have an interface, a wall, NEMA 15 wall socket that you can plug your different objects into. Same thing with here. You can plug an array list into a list. You can plug in a linked list to a list. It's the same idea.
It's the idea of not getting too specific if you don't have to.
Exactly. In fact, you want to not be specific.
You want to
a
be
lot.
vague as possible.
You want to
Not
be
specific.
while still giving you all the functionality you need. Great.
I've just solved the whole riddle to programming. That's it.
Something like that. Any other questions?
You have no idea what you're talking
It's okay.
No idea.
That's it. Just be very vague.
Any other questions?
That's how to avoid jail too. Be real vague.
Doing well?
Doing good.
Good. So some of this was a review. I think it's good to go over this again because it's hard to, I guess, overstate how important this is. Most programmers do not realize this. A lot of them don't. All right, so that's all for today. Go and get started on your lab, and we'll talk a little bit more about iterators next. Yes?
My lab.
Okay.